Welcome to Wings of Aero Advanced Education and Research Organization. To know more, visit our official webpage www.wingsofaero.tv. Today my topic is flow over an finite wing under an incompressible flow, followed by a topic of BIOT-SAVART law, Helmholtz's theorem, general lift distribution, PRANDTL'S classical lift line theory, and downwash and induced drag. Here first comes a finite wing. The question is, why are the aerodynamic characteristics of finite wing and the airfoil section are different? See a figure shown in your displayed in your screen. The flow over an airfoil is a 2D, and whereas a finite wing is a 3D body. So there is a component of the flow from the wingspan directions, so which generally forms a top and the front view of an wing. So here you can see a front view of an wing where the downward or beneath the wing causes a high pressure and the above the wing it causes a low pressure. Due to indifference in pressure and the imbalance, what it causes, the flow near the wing tip tends to curl on both the sides. However, the difference in pressure difference or an imbalance in pressure leads to cause a curl or a causes of trailing vortices at the tip of the wing, or it can also call as a circulation. So we can see that due to this span component of the flow, the tip to root, it causes a streamline over the top surface and are bent towards the root. So what you can say that found that it causes a trailing edge vortices at the tip. So this wing tip can be recovered by creating an winglets to reduce the induced drag. Now let's focus more about the effect of downwash. The wing tip vortices downstream of the wing, which causes a small induced component of a air velocity, which called as a downwash, indicated by a symbol small w. So this is an airfoil. So this is along the chord, leading edge to trailing edge, and this here along this line we have an, and from the angle between the chord and the relative vane, it causes an effective angle of attack, and the summation of effective angle of attack and the induced drag is called as a geometric angle of attack. That is alpha equals to alpha effective plus alpha I. So from there we can write effective angle of attack is equals to alpha, that is geometric angle of attack, minus induced angle of attack. Now what is meant by induced drag? A tilt backward of the lift vector induced by a drag is called as an induced drag. This is a type of an pressure drag. So we can write what is a total drag then? Total drag is a profile drag plus the addition of induced drag. So capital CD equals to small cd plus CDI, whereas CDI represents that DI by half rho V square of S. The half rho V square of S is can also be called as a dynamic pressure or denoted by a term as small q infinity. Now comes a BIOT-SAVART law. So in as per competitive exam point of view, they ask MCQ questions of match the following of various laws. So and with the formula, you have to be clear with the formula. So what happens, the velocity at a point as displayed in your screen, a point there at inducing a small velocity over there by a direction along the segment of DL. A curved film with a strength of gamma. So that is a circulation, and the distance between the point, the film, the vortex film strength and the point is distinguished by R. So according to BIOT-SAVART law, we can write as dV equals to gamma dl cross r by 4 pi r modulus of q. And this theory is also implemented or applicable only for in viscid and incompressible flow. The velocity induced by the point P is a straight line and the infinite vortex filament. So that time we can write as V equals to gamma 2 pi of h. Similarly, if the velocity induced at the point P by a semi-infinite vortex filament, then we can write as V equals to gamma 4 pi into h. These are an important formulae. They ask a few MCQ questions from this concept. Now comes Helmholtz vortex theorem. So far they have mainly two important points. The strength of a vortex filament is constant along the length. So whatever the length you are considering, the vortex strength will be constant throughout. And the vortex filament cannot aim in a fluid, and it extends to a boundary of a fluid or a closed path. Now comes lift distribution. You have to well know about the aerodynamic twist, aerodynamic geometric twist, wash in, wash out. So what is the basic of geometric lift? A different allofoil section will have a different geometric and aerodynamic twist, and the result of the lift distribution will vary along the span. Now what is geometric twist? Geometrically twist so that the angle of attack is different at different span-wise location. That is called as geometric twist. Now what is wash out? If the tip is lower angle of attack than the root, we call as wing is said to be wash out. Now what is wash in? If the tip is a higher angle of attack than the tip, than the root, the wing has wash in condition. Now what is aerodynamic twist? Different airfoil section along the span with a different value of alpha, when the CL equal to 0 is called as aerodynamic twist. These are important questions they might ask, and match the following from this respective notations. Now comes an important Prandtl's classical lift line theory. In this first will come with the assumptions. When this lift line theory is implemented. The first thing is when the flow is three-dimensional, steady and potential flow. And in addition, it is an inviscid, incompressible and rotational flow. Next comes when we are considering a high aspect ratio wing. That means the value of the aspect ratio is higher than 6. And low swept or a low swept angle. Next comes a small cross flow along the span. Now comes a Prandtl's classical lift line theory. Now this is a wing as shown in figure. From the center root part, we are considering the port side as h by 2 and the y direction another side is positive h by 2. Now we can see it forms a horseshoe vortex. Now what is a horseshoe vortex? It is a combination of bound vortex and two free vortex as shown in figure. Along the chord we will have a free trailing vortex from both the side, because the down we have a high pressure which is moving to a low pressure, so it is moving in a clockwise direction. But whereas from here in this side, that side we have a high pressure and upward we have a low pressure, so this is in anti-clockwise direction. Now the bound vortex induces no velocity along itself. However, the two free vortex contribute a downward velocity along the bound vortex. On the y-axis, we get this form. Now coming to an infinite number of horseshoe vortices. So what happens? The small strand, that is d gamma, are superimposed in the form that boundary vortex or single line is called as lifting line. So what happens here? They have a finite number of vortices over here. So each having a individual or small change in strength. So but combinedly we are considering they have a single vortices and the vortices remains constant throughout the filament. So that is mean by an lifted line theory. So accordingly we can write that the lift coefficient is Cl equals to A naught of alpha, that is 2 pi alpha. Now you know what is alpha? We have already known that is alpha effective plus alpha L equals 0. But here since it is induced we get is negative. And from there we can rewrite the equation as this. This is an integral form of fundamental equation of Prandtl's lifted line theory. Mainly the solution gives us 3 aerodynamic parameters for an finite wing. Now comes an elliptical lift distribution. These are the basic formulas for elliptical lift distributions, and the last one says that there is a zero lift produced on the wing tips. Now comes a downwash angle. A downwash is denoted by negative of circulation by 2b. Now this says that a downwash is constant over the span for an elliptical lift distribution. But whereas we have an induced angle of attack, the formula is alpha I equals to minus Cl by pi AR. What is a AR? Aspect ratio, that is B square by S. Now coming in consideration of induced drag, we get as CDI equals to CL square by pi AR. This is a very important formula. From this we can come to a conclusion that which states that the CDI is proportional to the square of CL and the CDI is inversely proportional to AR. That means if the aspect ratio is high, then we can decrease the induced drag. Aspect ratio, we can decrease the induced drag. Here comes some few demos. High aspect ratio will lead to a low induced drag and low aspect ratio will lead to a high induced drag. So you can see also for an elliptical lift distribution, the chord must vary elliptically along the span and the wing platform is elliptical. I hope this session was very useful for you guys. Subscribe to my channel for more updates and share this video with your needy fellows. Stay blessed. Take care.